This is a video demo of the principle of conservation of momentum. Momentum is connected to that idea that a body in motion tends to stay in motion. An object's momentum is calculated by multiplying its mass and its velocity. The momentum is often designated by the letter P. Often one designates a set of objects of interest. Here we call that set the system. The system's momentum is then just the sum of the individual objects' momenta. The system establishes a notion of internal forces, interactions between two objects within the system, and external forces, interactions between an object within the system and a body outside the system. The principle of conservation of momentum states that in the absence of external forces, the system's momentum does not change. Thus we can designate two times, before and after, and the momentum before should equal the momentum after. In our demo, our system will consist of two carts, each half a kilogram in mass. In the before, cart 1 will be moving and cart 2 will be stationary. Thus the system's momentum before will be equal to just the mass of the first cart times its velocity, since the second cart does not contribute. The carts have some Velcro and stick together after they collide. Hence the carts have the same velocity after the collision, and the system's momentum can be calculated as the sum of the two masses times their shared velocity. A motion sensor placed at the start of the track records the velocity of cart 1 throughout the demo. The trial video begins with a top view of the stationary cart 2, with cart 1 approaching and then colliding with it. A sped-up version of the video brings out the change in speed. A slow-motion version of the video brings out the more complicated interaction as the Velcro is taking hold. Next we will look at a graph of cart 1's velocity versus time, as recorded by the motion sensor. Note the three distinct regions of the graph: before, when the carts are separate; during, the fast fall-off, when the carts are establishing their connection; and after, when they are connected and proceed as a unit. We will take the last before velocity and the first after velocity to use in our calculations testing the conservation of momentum. Recall that the system's before momentum has only a contribution from cart 1. Its mass of half a kilogram times the before velocity of 0.2444 meters per second yields momentum of 0.122 kilogram meters per second. After the collision, when the two carts stick together, the system momentum is the product of their combined mass and their shared velocity. The combined mass of the two carts is 1 kilogram, and the after velocity of 0.1229 meters per second lead to a momentum of 0.123 kilogram meters per second. A comparison of the momentum before and after shows that they are quite similar, and meets with the expectation that the momentum is conserved. That is, the momentum does not change with time. The previous result was a little too good to be true. Let's try another run. Again, we will look at the velocity versus time data. As seen previously, we have the before, during, and after regions, and we select out the last before velocity and the first after velocity to use in our calculations. The before momentum is the mass of cart 1, half of a kilogram, multiplied by the before velocity of 0.2954 meters per second, giving a momentum of 0.148 kilogram meters per second. The after momentum is the sum of the masses of cart 1 and cart 2, a total of 1 kilogram, times the after velocity of 0.1377 meters per second, producing a momentum of 0.138 kilogram meters per second. A comparison of the before and after momenta is not as close for this trial, having a percent difference of 7%. Let us think about this. Recall that the conservation of momentum principle only applies in the absence of external forces. But we do have external forces, those being friction and air resistance, as evidenced by the slight downward slope seen in the before and after regions of the graphs. The friction and air resistance were always present, but the during phase of the collision was relatively short so that they did not have a substantial effect. Still, the external forces were present and can explain a slight reduction in momentum.